Hey everyone, and welcome. Today we are diving into a really fundamental data structure, something every computer scientist should know, the AVL tree. It's kind of the secret sauce behind some of the fastest software you use every single day. So let's jump right in and see how it all works.
I mean, really think about it for a second. You can search for something across millions, even billions of items online, and you get a result back in like a fraction of a second. How on earth is that possible? It's definitely not just about having a super fast computer.
Well, the secret is this really elegant idea called balance. By making sure our data is organized in a very specific, balanced way, we can make searching through it incredibly fast. And that's precisely the job of an AVL tree.
But, to really get why AVL trees are so cool, we first have to understand the problem they were designed to fix. So let's take a look at what happens when things get, well, out of balance.
So, you've got your standard binary search tree, or BST, and in an ideal world, it's fantastic. It's bushy, it's wide, and finding data is super quick. But here's the worst case scenario. If you happen to add data in a sorted order, the tree just degenerates into this long, spindly chain. It basically becomes a linked list, and when that happens, searching is a total nightmare. You have to check every single item, one by one. That's what we call an ON operation, and trust me, it's a massive performance killer. And this is where our hero, the AVL tree, enters the scene. It's a special kind of binary search tree that is self-balancing. It was named after its inventors, Adel-Cinvelsky and Landis, and it has these clever, built-in rules that stop that worst-case scenario dead in its tracks. Okay, here's a really simple way to think about it. An AVL tree is basically a BST with a personal trainer. It's never lazy. After every single operation, whether you add something or delete something, it checks its own structure. If it senses it's getting a little lopsided, it immediately does a quick workout to get right back into perfect form. So how does this personal trainer know when the tree is out of shape? Well, it follows just one simple, elegant rule. And that rule is all about something called the balance factor. For any node in the tree, we calculate this by taking the height of its left subtree and subtracting the height of its right subtree. And just a quick reminder, when we say height, we mean the longest path of edges from that node all the way down to a leaf. So here's the deal. For the tree to be considered balanced, the balance factor of every single node has to be either -1, 0, or +1. That's it. A -1 means the right side is taller by 1, a +1 means the left side is taller by 1, and 0 means they're perfectly even. But the second a node's balance factor hits -2 or +2, ding ding ding, we've got an imbalance, and the tree needs to fix itself right now.
So what does it do? This is where the magic really happens. The AVL tree has these 4 powerful moves called rotations, and it uses them to restore balance almost instantly. Let's see them in action.
All right, let's get our hands dirty with a real example. Imagine we insert the number 30, then 20, then 10. What we get is this tall, skinny chain. So let's calculate the balance factor for the root node 30. The height of its left subtree is 2. That's the path from 30 down to 10. The right subtree is empty, so its height is 0. 2 minus 0 gives us a balance factor of +2. And boom, that's a violation of our rule. This specific pattern, by the way, is called a left-left case. To fix this, we do a single right rotation on that unbalanced node 30. So imagine grabbing node 20 and pulling it up to become the new root. As you do that, 30 gets pushed down to become the right child of 20. And just like that, check it out. The tree is perfectly balanced. Every node now has a balance factor of 0. And you can see the whole tree is shorter and more compact. Much better. Now, the right-right case, or RR case, is just a mirror image of what we just saw. If we had inserted 10, then 20, then 30, we'd get an imbalance to the right with a factor of -2. The fix is perfectly symmetrical. A single left rotation snaps everything back into place. Okay, so those were the easy ones. Now for the slightly trickier zigzag cases. These are the left-right and the right-left cases. They actually need a double rotation to fix. Just think of it as a 2-step move. First, you do one rotation to straighten out the zigzag, and then you do a second one to balance the whole thing. So really, it all comes down to recognizing one of these 4 patterns. This here is your cheat sheet. For a left-left case, you do a right rotation. For a right-right case, you do a left rotation. For the left-right zigzag, you do a left, then a right rotation. And for the right-left zigzag, you do a right, then a left rotation. That's it. This covers every possible imbalance.
Okay, so we've been doing all this work, calculating balance factors, performing rotations. What's the point? Why bother with all this? Well, the payoff is huge. It's all about guaranteed speed. Just look at this chart. For a standard BST, in the worst case, searching for one item out of n items could take n steps. That's linear time, or O of n. But because an AVL tree is always balanced, its height is guaranteed to be logarithmic. Searching takes, at most, O log n steps. To put that in perspective, for 1 million items, a bad BST might have to look through all 1 million of them. But an AVL tree, it would take, at most, maybe 20 steps. I mean, the difference is just staggering.
And this awesome logarithmic performance isn't just for searching. It holds true for all the major operations. Searching is O log n. Insertion is O log n, since that's just a search plus a few quick rotations, and deletion is also O log n. This consistent guaranteed efficiency is the whole reason we use AVL trees.
Let's put them side by side one last time to really drive this home. A standard BST, yeah, it's simpler to code, but you get absolutely no guarantee of balance. Its performance can drop to O of n. An AVL tree is more complex, for sure, but in exchange you get an ironclad guarantee that all your key operations will be fast, always O of log n.
And that brings us right back to where we started. This guaranteed speed is exactly why AVL trees and other self-balancing trees like them form the backbone of things like high-performance databases, file indexing systems, even the routers that direct traffic on the internet. They prevent the exact kind of performance slowdowns that would make these systems totally unusable at scale.
All right, now it's your turn to be the personal trainer. Let's do a few quick exercises to see if you can spot the imbalance and call out the right fix.
Okay, first one. If you insert 50, then 20, and then 10, what kind of imbalance do you get, and what's the fix? So if you visualize that, it's just a straight line going down and to the left, right? That's our classic left-left case, which needs a single right rotation.
Okay, how about this one? We insert 10, then 30, then 20. Now think about that path. 20 is to the left of 30, which is to the right of 10. You see that little zigzag? That's our telltale sign. This is a right-left case, which needs that double rotation. A right rotation first, then a left rotation.
And for our last one, what if we insert 20, then 40, then 50? What's that pattern? Yep, it's a straight line down to the right, which is a right-right imbalance, and the fix for that is a single left rotation. If you got all of those, fantastic. You've really got the hang of AVL rotations. The key is just recognizing the pattern. Great job today. Thanks for joining me, and happy coding.